Okay, Math 31's sketch f of x. When f of x is x minus cos x without a calculator. We're going to do it from 0 to 2 pi. So our domain is given to us 0 to 2 pi. Our intercepts. Our x-intercept, this will be given because it's a weird one. If it's ever a non-calculator type of question, or like you can't do it algebraically, it will always be given. But this one we could just plug in. Okay, then we have symmetry. There's none by plugging in negative x. 4. Okay, asymptotes. With trig there could be. So you need to check for non-permissible values. For here we don't have anything in the denominator, so there's none. Intervals. So remember, intervals of increase and decrease, we need our first derivative test. So let's go and find our first derivative test. Intervals of increase and decrease. So what is f prime at x? Well, the derivative of x is 1, and the derivative of negative cos is positive sine. So there's our derivative. Our critical values. A lot of you on your exam forgot to say that my critical values come from making my derivative equal to 0. That's important to state. So a lot of you lost marks for that. I want it to be perfect. And so we get sine of x is equal to negative 1. In our domain, we know that happens at 3 pi over 2. Again, that comes from our unit circle. We know how to find those values. So we set up our chart. And again, some of you weren't executing your chart very well either. We have from 0 to 3 pi over 2, and then from 3 pi over 2 to 2 pi, because it's a closed interval. With a closed interval, remember, we can now have absolute maxes and mins, potentially. So let's say for checking out what's happening to my derivative, to tell me what's happening with my original function, that's our goal. So if I use x is equal to pi here, okay, so that's something between 0 and 3 pi over 2. 1 plus sine at pi, what is pi? It's just 0, so we're going to get 1. And so it's increasing. Okay, if I choose something between 3 pi over 2 and 2 pi, remember that's basically just quadrant 4. So something like 7 pi over 4, I like the pi's over 4 is nice. What you end up getting is 1 plus root 2 over 2, which is a positive. We don't need to evaluate it. So increasing. So there is actually no max or min between here because we're increasing the entire time. Okay, from 0 to 2 pi, it's going up the entire time. Gives us an idea of what the shape might look like. Then we have to check our max and mins. Okay, but we do know what those end points are, 0 and 2 pi. We want to know what those values are, the end points, which we will graph. Then we're going to check our concavity. And points of inflection, and I'm assuming with a trig function there's going to be some points of inflection. I don't know how many, probably 2 to 3. So we need our second derivative. What's f double prime of x? It's just going to be cos of x, so nice. And now we can find our critical values. Again, that is setting f double prime at x is equal to 0. So 0 equals cos of x. In our domain, when does cos x equal 0? That happens at the top and the bottom on our y-axis. So x is pi over 2 and 3 pi over 2. So we're going to have 2 critical values that we're going to put into our interval chart. So here's our chart. We are checking what's happening to Okay, I'm gonna be fat now. Okay, I can't get my pen to switch to thin, so I have all types of fun today. Okay, so we have my interval, and then I have my f double prime of x, and what's happening to f of x. So we are going to have from 0 to pi over 2, so that's quadrant 1. We are going to have pi over 2 to 3 pi over 2, and then we are going to have from 3 pi over 2 to 2 pi. And I don't even need to pick values because I know I'm in quadrant 1, and cos x in quadrant 1 is positive, so it's concave up. What do I know about here? In this one, this is quadrant 2 and 3, and I know it's negative, concave down. And then again, over here, this is quad 4, and cos, which is x, is positive, concave up. 2 points of inflection. What are they? Remember, we actually have to find them. Ah, yes, there it is. Okay. So we are going to have at x is pi over 2 and x is 3 pi over 2. Remember, f prime at pi over 2 equaled 0 and f double prime at pi over 2 sorry, did not equal 0. Shoot. I'm thinking about the 3 pi over 2. So made this one 0, but was nothing. So this is a regular inflection point. But for this one, f prime at 3 pi over 2 equaled 0, and f double prime at 3 pi over 2 equaled 0. So it's a horizontal inflection point. So we know how those inflection points, what they will kind of look like. So here we go. Let's make a graph. What's interesting about this one is both our x and y's are going to be in radians or in terms of pi. Okay, so I set up my x and my y. So what we know was that we had a y-intercept at -1. So there it is. We have some random intercept at 0.7 something. Then we have another point at pi over 2, sorry, and I didn't show that. Finding our pi over 2, so we actually have to find our y values all the way here. So we defined what they were, but we forgot to plug them in and see what they actually were. So f at pi over 2 works out to be pi over 2, and f at 3 pi over 2 works out to be 3 pi over 2. I also wanted to find my endpoints. We already found that f prime at 0 was -1, but what is it at 2 pi? We get 2 pi minus cos at 2 pi, which is 2 pi minus 1, which is approximately 5.28. Just to give you guys some more numbers. So we found all our endpoints. So I will put that over here. So pi over 2 minus, and our endpoint at 2 pi is just a little bit short of 2 pi. Okay, at 3 pi over 2, we had that 3 pi over 2, and that was our horizontal inflection point. This one was just our regular inflection point. So up until here, our graph was concave up, but then it switched to concave down. And then we had that elongated horizontal inflection point to our end point. And there is our graph of our function. So that's the end of 7.2. Let's talk about derivatives, which is 7.3 of all the other kinds. I'm just going to write them out because technology's not been my friend today. Again, in calculus and post-secondary, you don't get formula sheets. So you just need to know these. So the derivatives of tan is secant squared. Cosecant x is negative cosecant. Cotangent x. Secant x is secant x tan x. And again, you don't need to know the proofs for any of these. You just need to know them. So let's just try a couple examples. Let's differentiate. F of x is 1 over 1 plus tan x. For this one, what I would do is bring up that 1 plus tan x and make it negative 1. Then we have our chain rule. We bring down that negative 1, reduce our exponent by 1. Then we take the derivative of the inside. The derivative of 1 is 0, and the derivative of tan is secant squared x. Move that tan back to get negative secant squared x. Let's try another one. Y equals 2 cosecant cubed 3x squared. So here we have chain rule first. If you want to write this one a little bit differently, just remember it's only the cosecant being cubed. So that's where you'll see the chain rule. So we're going to get 6 cosecant squared of my 3x squared. Don't touch your angle. Take the derivative of cosecant now, which is negative cosecant of my angle, cotangent of my angle, because the derivative of cosecant is negative cosecant, cotangent. Notice they don't have cubes or squares on them. You don't need to. It's just the derivative of the trig function. We already did the chain rule. And now we have to multiply this by the derivative of our angle, which is 6x. And there's our derivative. I could collect a little bit of like terms. The 6's can be multiplied together to get 36x. Bring that x to the front. We do have a negative in the middle, so let's pull that negative out. And we just have cosecant of 3x squared, cotangent of 3x squared. And then we have cosecant, again, squared of 3x squared. We can't collect like terms because actually we can. We'll go one step further. And these are being multiplied, so we get cosecant cubed 3x squared, cotangent 3x squared. And that's our final answer. Okay, so lots of stuff with these ones. Let's do one implicit with tan. Okay, so here the derivative of tan is secant squared of our angle times the derivative of the angle, right? And the derivative of the other side is 2x. So we're going to get dy dx equals 2x over secant squared y. Use your identities. And what we end up getting, dy dx, is 2x cos squared y. I can move an extension to this. I can say find the slope of the tangent line, but we will leave it there. That's as far as I will go for this week. Please make sure that you do try a lot of these. In post-secondary, when you do calculus, you will be doing trig within your other units as well. So they do it when they teach derivatives. You will do trig derivatives with them. In AP calculus, we do extensions of trig. We do inverse trig functions, which you will also do in post-secondary. So I will stop there.